Hello! The purpose of this video is to review how to solve problems that involve the densities of gases. You'll recall in class that we derived an expression that tells how the density of a gas is related to other measurable properties, and that expression is d equals mp over RT, where d represents the density of the gas in grams per liter, m represents the molar mass of the gas in grams per mole, p represents the pressure in atmospheres, T represents the temperature, and R, of course, is our friend the gas constant. You don't need to know where this came from, but if you're curious, the derivation is given in your textbook. Here's an example of a simple problem. What is the density of nitrogen gas at a temperature of 28 degrees Celsius and a pressure of 2.50 atmospheres? Well, since we're asked to find the density, we don't need to do any algebraic manipulation. Since the equation already has density isolated, we'll simply need to plug in values for the molar mass, the pressure, and the temperature. Nitrogen is the gas that we're trying to find the density of, and you'll recall that nitrogen is a diatomic molecule, is a pure element, so that means the molar mass is going to be 2 times the molar mass found on the periodic table, or 28.02 grams per mole. We know that since we're using the gas constant R, which has units of liter atmospheres per mole Kelvin, temperature must be converted into Kelvin, so we'll do that by taking 28 degrees Celsius and simply adding 273, because we know the 0.15 is going to round off, to give us a temperature of 301 Kelvin, and now we can simply plug in. Density equals molar mass times pressure over RT, 28.02 grams per mole, 2.50 atmospheres, 0.08206 liter atmospheres per mole Kelvin, times our temperature of 301 Kelvin. Oh, let's see. Moles cancel moles. Atmospheres cancel atmospheres. Kelvin cancels Kelvin. And I'm left with units of grams per liter, which makes sense since I'm trying to find the density. And I get a value of 2.84 grams per liter as my density of nitrogen at this temperature and pressure. We can use the expression rearranged to find one of the other variables, for example, molar mass, pressure, or temperature. As an example of that, I could ask, at what pressure will krypton gas have a density of 4.00 grams per liter at a temperature of 125 degrees Celsius? Well, I'll begin by writing out the expression as I'm given. Density equals mp over RT. Since I'm trying to find pressure, I'm going to cross multiply, and I get density times RT equals molar mass times pressure. And then to get pressure by itself, I'll divide both sides by molar mass. And that gives me my rearranged expression. Pressure equals density times RT over molar mass. Since I'm given temperature in degrees Celsius, I'll need to convert that into Kelvin. So I'll do 125 degrees Celsius plus 273 gives me a temperature of 398 Kelvin. And now I can plug in. The density is 4.00 grams per liter. R as its usual value in units. Temperature is 398 Kelvin. And I'll divide that by the molar mass of krypton, which I get from the periodic table, as 83.80 grams per mole. Oh, liters cancel liters, grams cancel grams, moles cancel moles, Kelvin cancels Kelvin, I'm left with atmospheres, and I get as my final pressure 1.56 atmospheres. Now, one of the most useful applications of this expression is to find the molar mass of an unknown substance. Basically, if you have any chemical compound and you can get it into the gas phase and you can measure its density at a given temperature and pressure, you can calculate its molar mass, which is really useful. So in this problem, we asked the gaseous compound has a given density at a certain temperature and pressure, calculate the molar mass. So I'll begin by writing down density equals mp over RT. Cross multiply, density times RT equals molar mass times pressure. Now divide both sides by pressure to isolate molar mass. And I get molar mass equals density times RT over pressure. I'll plug in my density, R, temperature, 342 Kelvin, divide that by the pressure of 99.6 kilopascal. Oh, wait a minute. Got to convert that to atmospheres. So I'll embed the conversion factor, 1 atmosphere over 101.325 kilopascals. Kilopascals cancel, atmospheres cancel, kelvins cancel, liters cancel, and I'm left with grams per mole. That gives me a molar mass of 108 grams per mole. Now, one of the coolest applications is this. You may recall that when you calculate the empirical formula of a compound, if you want to go from the empirical formula to the molecular formula, the added piece of information you need is the molar mass. Well, guess what? You just calculated the molar mass of this compound, so I can further ask, if the compound in the previous problem has an empirical formula of C2H3, determine the molecular formula of the compound. Well, this is a review from a couple of months ago, but you should remember this. The molecular formula is the empirical formula multiplied by some integer x. That integer x is simply the ratio of the molar mass to the empirical formula mass. In this problem, you were given the empirical formula, but I assume that you know how to calculate it if you're given the masses of each element present in the compound or the percentage composition by mass. If not, go back and review. In this case, because my empirical formula is C2H3, the empirical formula mass is 2 times the molar mass of carbon plus 3 times the molar mass of hydrogen, or 27.04 grams per mole. So to find x, I'll simply take the molar mass I calculated in the previous problem, 108 grams per mole, divide that by the empirical formula mass, 27.04 grams per mole. This will always give you something very close to an integer. In this case, the integer is 4. So to finish the problem, my molecular formula is the empirical formula, C2H3 multiplied by 4, or distributing the 4, C8H12 is the molecular formula of this compound. Not so hard. All right, that's it for today. Good luck.